Hi everybody and welcome to part 13 of the Bravo project. Today we will be building our control logic, which is essentially our last module in the project. And this module is quite straightforward. We have a couple of registers here, and also we have two control ROMs. And of course we have a bunch of other gates here that we're going to talk about. Now, this module will be the last piece of hardware that we are building in Bravo project. And from next video, we probably going to be focusing more on the software side by loading, some operating systems and looking at some programs. And maybe later on, we could just go deeper on the software side and look at developing microcode and come up with, some opcodes and so on that we could develop as an example. So with that, let's get started and have a look at the couple of slides, which I go through basically some theory, and then after that we're going to look at the circuit logic, and then we're going to go ahead and build this module, and finally we're going to test that module today. All right, let's get started. All right, so let's have a look at a couple of slides and build a foundation for today's circuit. First thing is, what is a control logic? Well, control logic is basically a part of the computer which is outputting the control signals based on each specific instruction, right? So we are running, let's say, a program, and we have some instruction in it. And for each instruction, we need to actually output some control signals so that those control signals go to different modules in our computer and basically enable input and output for those modules, right? So far, we have been using our Arduino Mega Shield and some sketches to basically control those signals, right? I mean, we had like some signals high and some signals low. For example, let's say we wanted to output the content of the B register on the bus. We were just, bringing the BO line high because that was an active low signal. And this way we would, control basically the output of the B register. Now, obviously, in the final version of the computer, we don't want to have an Arduino Mega or any sketch there, and everything should happen kind of automatically in the background. Therefore, we are actually building a control logic here. So with that, let's see how a computer actually executes a program, right? So when you turn on a computer, and probably we're mostly talking about the Bravo and other similar 8-bit computers here. But when you turn it on, it all starts with our program counter, right? So the program counter is the first module which actually starts counting. And if you remember from our program counter video, this is basically a 16-bit binary counter that starts counting from 0. Now, when this program counter counts, obviously it's going to have some output data. And if you want to put that, let's say, value on the bus, we were using the counter out or CO signal to put that basically data on the bus. Now, the next step is the memory address register, which actually needs to read that value, which is on the bus now, and read it in so that it could address our memory. And basically, this is the next step in the process where MAR or memory address register read the value from the bus, and using that value, it could address our memory, right? So now that we have actually a value in our MAR, we basically have an output on the MAR circuit, and therefore we are addressing a specific memory address in our memory, right? Now, whether this memory is the flash or the RAM chip, it doesn't matter. The point here is that we are actually addressing some sort of memory. Now, in case of Bravo, we actually have the circuit designed in a way that when we start the computer, when we're actually pointing to address 0, that's going to be pointing to our flash. Normally, you would be probably pointing to a flash memory or an EEPROM so that you could actually boot the computer using some instructions at the beginning. And that's why normally in most of the computers, the first address is actually pointing to some sort of a non-volatile memory, which could save some instruction in it, right? So in case of Bravo, we are pointing to flash, and basically we are addressing the memory. And once we address that memory, then obviously we're going to have some content in that memory address. And that content, if you want to actually put that content on the bus, then we're going to use a signal called RAM out, right? And of course, for the memory address register, I guess I forgot there, we have a memory in signal when you want to actually read the value of the program counter into the memory address register. Again, at this stage, normally another thing is going to happen, and that's when we actually need to step our program counter to next step. And because all the programs are actually executed in a sequence, we need to basically move the program counter to the next step. And that's why you see this next step basically instruction, or let's say control signal here, which in case of Bravo we actually call it CEME, and that means that we are doing the count enable and also a memory enable at the same time. Now the count enable goes directly into our program counter, and basically it just steps the program counter to the next step. However, if you remember, we also had the memory address register, which was again a 16-bit binary counter, and therefore we kind of need to keep those in sync, at least at this stage. That's why we are going to do the same thing using the memory enable signal, which basically just steps the memory address register module to the next step. Now the point is that after doing all of these steps, what we have here is really a value in our memory that needs to be put on the bus, and that's done through RAM out. However, that value which is on the in the memory could be either an instruction or could actually be a data. If it's an instruction, then we kind of read that into our control logic, and basically that's the part that we'll be talking about today, and we're going to go through different register in there. But if it's a data, then that data is normally going to, let's say, A register, B register, or maybe even to another address of the memory. So let's assume that after these couple of steps, we actually have an instruction here inside that memory space or memory address. Now, the next step would be to actually read that instruction from the bus into our control logic. And specifically, inside the control logic, we have a section which is called instruction register. And the signal to do that is normally called instruction in, or II. So that means that whatever instruction that we have right now in the memory should be read into our instruction register part of our control logic. Now, our control logic actually has two more sections here, as you can see on the screen. One of them is called a flag register, and flag register is basically responsible for saving the latest status of our flags. So if you remember from our ALU module, we had some flags based on the operation that we were doing on ALU. We had outputs on the flag lines, right? So we had 0 flag, we have carry flag, let's say, and then also we had the negative flag. So those flags needs to be saved somewhere. Otherwise, if we don't actually save them in a register, because our program is actually executing back to back and it's going to go to the next step, we're going to lose the status of those flags at that moment of time. So let's say that we have done an operation in ALU, and now we set the let's say negative flag to 1. So at this point, if we don't save the status of a flag somewhere, then with the next execution of the next step, what we're going to happen, maybe we're going to lose, we have a result that we actually override that, let's say, 0 flag or negative flag, and we're going to lose the status of the flag. Therefore, each time that we're actually doing an operation and there will be some flag outputs, we want to save the status of those flags, because those flags could be used for conditional jumping or for other decisions that we could make later in the program. So therefore, we have a small register called flag register, And the signal to do that is normally called a flag in, or FI, that actually saves the status of those flags. So we talked about these two parts. The only part that remains is really a micro step counter. Now, each instruction that is actually executed in the computer have some what we call it micro steps, right? And we're going to go into more details in next slides. However, each instruction have 16 steps, and this little binary counter, which is a 4-bit binary counter, is actually responsible to count those micro steps. So in general, think about it that the program counter is actually counting, the major steps or the main steps in our program. However, the microstep counter is actually counting the micro steps on each instruction. Now, the cool thing is that the output of all these three sections here, flag register, instruction register, and microstep counter, could be combined all together as one output, which in case of Bravo, it's a 13-bit output. And we could use those to actually address some control ROMs. Now, control ROMs are basically either an EEPROM or a flash memory chip, which has already been programmed with some microcode in them. And the only thing that you need to do during the execution is really to address them using, the output of these registers and this counter. And basically, once you address those ROMs, they will be outputting our control signals. All right, so I know that it may be a little bit confusing, but let's move on to the next slide that may be more clear here. So again, as I said, we have the flag register, which is actually a 3-bit register because we have 3 flags, right? 0, carryout, or negative flag. And the signal in Bravo to actually control this flag is called EOFI. And EO should be familiar to you because this is basically sigma out or sum out signal that we were using in our ALU module. However, we kind of use the same signal here to actually input the flags into our flag register. So essentially, EOFI is the same signal. It's a single signal that does 2 things at the same time. When we have this signal high, it's going to output the content of the ALU on the bus, and at the same time, it also saves all the flags into our flag register. Now, the next part is instruction register, and as I mentioned in the previous slide, and normally the signal for that is instruction in, or II. However, in Bravo, we actually are using a combined signal, which is a combination of the HI plus CEME. And whenever we have both of those signals set to high, that means we actually have an instruction in register. Now, that's a little bit confusing here. However, we're going to have a look at why we are actually combining the signals in the next slide. But for now, just imagine that whenever we want to have instruction in signal active and basically read the content of the bus into our instruction register, then we need to bring both HI and CEME high at the same time. Now, instruction register itself is a 6-bit register, meaning that we could actually have 64 different type of instructions in general in Bravo, right? So with 6-bit, you could have a total number of 64 different type of combinations, and that means that we could have 64 different type of instructions. So that is basically our instruction register. And finally, again, as I said, we have a microstep counter, which is again a 4-bit binary counter, which is continuously counting from 0 to 15. Now, the output of all of these, 4-bit here, 6-bit here, and 3-bit here, will be 13 bits. And we're going to use that 13 bits to address our control ROMs. Now, if you are one of those who actually built the Ben Eater's 8-bit computer, you remember that in control logic, we actually use some EEPROMs in that circuit. However, here we are using flash memories, just similar to what we use in our memory module. And these flash memories are actually a lower capacity version of the chip that we use in our memory module. These are the SST39SF010, which are only 128 kilobytes. And honestly, we will be using only 8 kilobyte of each of those chips when fully programmed. But again, this is the lowest capacity of these chips that are available in the market. And again, they are cost effective, so no problem there. However, again, these chips play the role of a read-only memory, meaning that once we actually wrote our microcode, then we're going to upload those to the chips. And then during the operation of the computer, our control logic, registers, and basically step counter, the combination of those three parts will be only addressing these ROMs. And based on the address, obviously, when they are programmed, there will be some, outputs on the output signals. Now, in case of Bravo, we have total of 16 control signals, and each of those chips actually have only 8-bit outputs, right? So that's why we are using two of those chips, and basically we call one of them the most significant byte, and the other one we call it a least significant byte. And these naming are just basically to kind of separate them from each other and being able to understand which control signals are, let's say, managed by MSB and which ones are controlled by the LSB. And that's pretty much it. It should be quite clear what is happening here. So let's move on to a bigger picture. And this is actually the slide that I showed you in the first video of the Bravo project when I was introducing the project. And I promised you that we're going to come back to this slide. And here we go. Today we need to actually have a look at this diagram again, and also in maybe next couple of videos when we're looking at the software, this diagram will be a very good reference to what is exactly happening. However, I'm just going to go through this diagram really quick to just remind you of different modules that we have built so far and how they actually relate to each other. So if you remember, we had obviously 8-bit bus in the middle. We had A and B registers that are both of them are 8-bit and connected to the bus. We had our ALU here, which again does our addition or subtraction operation, and it's going to have an 8-bit output again going on the bus. However, at the same time, we had three flags that are output of our ALU, as you can see, negative, carry, and 0 flag. And those actually come into our flag register here that I just talked about it. And then, of course, we have our instruction register here that is reading the instruction. Again, when the instruction is put from the memory address into the bus, it could be read into our instruction register. And finally, we have that little micro step counter here. And as you can see, the output of all these three sections are combined together, and that will be basically addressing our control ROMs, and our control ROM will be outputting our control signals. Now, we talked about the UART RX and TX module. Again, both of them are either reading or writing into our bus. We also talked about the program counter, which has basically the high byte and low byte, and basically I've talked about all of these modules in details in its related video. However, if you remember from program counter, we had a high byte and low byte concept, and basically because our program counter is 16-bit and our bus is only 8-bit, we actually needed two different clock cycles to be able to put all the content of the program counter on the bus. And the same thing for memory address register. On the input side, memory address register is also 16-bit, but the bus is 8-bit. So again, we needed two clock cycles to read actually the content into our memory address register. However, the output of the memory address register is actually directly connected to our RAMs, and that one is a 16-bit in general. So if you look at the whole circuit, I think it makes more sense after building all of different modules and going through testing each and every one of them. However, now we are kind of interconnecting all of those to each other and trying to make sense of what is actually happening here, right? Now, one important thing in regard to the control logic in Bravo is that we have a total of 16 control signals that are outputting from our control logic. However, some of those signals are what we call it combined signals. So let's first talk about it and focus on that and see why we actually have those combined signals. Well, the point is that if we didn't want to actually combine some of those signals, we needed to have more control signals coming out of our control ROM. Essentially, if we had dedicated signals for each operation, we kind of end up with probably 18 or 20 different signals, and just because of that 4 or 5 more signals that we needed here, we probably needed to add a lot of circuit to our control logic. However, when Carsten actually have designed the circuit, he has been very creative to come up with some solution in regard to reducing the number of signals. So essentially, he still wants to have exactly 16 signals on the control logic as an output. However, for the input signals that are actually building those output signals, he came up with a combination type of thing, meaning that some of those signals here are let's call them a derivative signal. They are not a direct output of the control signal or control logic. So let's have a look at one of them, and that probably makes it clear. So let's say that we want to have instruction in signal, right? And the instruction in is the signal that reads that instruction from memory and put it in our instruction register. Now, one solution would be to actually have a dedicated line here on our control ROM that outputs the II, or instruction in signal. However, we could actually combine 2 other signals and come up with the same signal. So in this case, in Bravo, we are actually combining the CEME and HI signal together, and that whenever we have both of those high, that means we are actually doing an instruction in. So I guess you got the idea here that sometimes by combining those signals, we could actually come up with more signals, right? So and now let's talk about another example here that probably helps us understand this, a signal combination a little bit better. Now, if you remember, we said that we actually needed 2 cycles, for example, for the program counter to put the content in the bus, right? So if we really wanted to manage that through 2 different signals, one signal for the high byte and the other signal for the low byte, then we needed to actually have 2 signals coming out of our control logic. However, what we have done here is that we get a HI signal, and then by combining the HI with the counter out, we could actually come up with those 2 signals. Since we have an HI, and actually HI signal goes through an inverter in our control logic, which we're going to look at that shortly in the circuit. So at each point of time, we either have HI or inverted HI, right? So if HI is available, and then we could combine that, let's say, with counter out signal, then we are actually using this signal, which we could call a COH, or counter out high, to output the high byte in our program counter. Now, as soon as we bring down the HI signal basically low, the inverted HI is going to go high automatically, and that is obviously when combined with counter out signal, then that's going to give us another signal which we could use for the low byte of the program counter. So as you can imagine, by just combining that HI signal, and all of those actually are a combination of an HI signal and some other signals, we could actually expand the number of output signals. So if you look at it here, the total number of input signals are like 1, 2, 3, 4, 5, 6, 7, and 8 signals and inputs. However, the outputs are about 10 signals. So we kind of gained 2 more signals here just by combining the HI signal with the others. All right, so with that, let's have a look at all of these combined signals, just to clarify everything here. So again, as I said, everything is actually combined with HI or inverted HI, which HI is a single signal, meaning that we actually have only one output from control logic, and we're going to use an inverter to make it inverted HI. So as you can see, we're saving one signal here. We are just outputting HI. However, with the help of that inverter, we could have inverted HI when actually the HI changes its value. Now, the counter out high is responsible for outputting the content of the program counter high byte on the bus. The counter out low is responsible for the same thing, however, for the low byte. Now, the counter in, when combined with HI, gives us 2 more signals, which means that counter in high, which means that reading the content of the bus into high byte of our program counter, and counter in low, it does the same thing, however, for the low byte. Now, on the memory address register, again, on the input side of that circuit, we needed to signal write. Memory in high is responsible for taking the content of the basically bus and put it on the high byte of the memory address register, and memory in low is basically responsible for the same thing, however, for the low byte of the memory address register. Now, another interesting case here is in regard to our basically RX and TX module in our UART module. Now, if you look at the control logics here, and I'm sorry, it's a little bit small, but we're going to have a look in details on all of those signals for now. But we actually have only one output from our control logic for the send and receive, and that's called the TR signal. So as you can see, by combining the TR again with HI and inverted HI, we actually are coming up with 2 signals. One will be controlling the RX module, and the other one will be controlling the TX module. So that means that at each point of time, either we want to read or, either we want to send or receive the data, we are actually just outputting the TR signal from control logic. However, depending on the condition of the HI signal, we are either receiving or sending the data. So that means that basically our UART module is actually a half duplex module, and that means that at each point of time we are either sending or we are receiving data, meaning that send and receive could not happen at the same time in Bravo. And then finally, for instruction in signal, we actually combining CME and HI. So again, as I said, whenever we have both of those signals set to high, then that means that we are trying to do an instruction in. And finally, we have another signal, and if you remember, this is actually the bank control signal in our memory module. If you remember, for controlling different banks in our memory module, we had a little circuit. We called it bank register, and that circuit requires some control signals. And at the time, I mentioned that we are actually combining 2 signals, which called the EC and HI. And when both of those signals are going high, that means that we are actually inputting something into that register. So again, if it is a little bit confusing at this stage, don't be worried about it, because we'll be working with those signals, and we're going to actually build some microcode, and It's going to make sense later that how these signals going to work and how we actually going to be outputting these control signals out of our control logic. Now, with that, let's have a look at a couple of simple instructions here that just to give you an idea. We have a fetch instruction, and hopefully you guys are familiar with the fetch instruction. This is basically an instruction that exists with at the beginning of any other instruction when a program is executing on a computer. And the purpose of these couple of steps at the beginning of each instruction is really to pull data from the memory or basically specify the next instruction that should be executed. So if you go back to actually the previous slide when I was talking about this slide here, you may have asked, okay, where these signals are actually coming from, because we, let's say, turned on the computer and we haven't even reached the control logic yet to read that instruction into let's say our instruction register and have an instruction to execute. So how the computer actually knows at the beginning that we need a CO, an MI, an RO, and CME so that it actually pulls the instruction for execution. Well, the point is that with every instruction that we are actually executing in the computer, there will be a couple of steps, or to be specific here, 3 steps or micro steps here that are called the fetch instruction. So let's have a look at this fetch instruction and see what is its purpose. So again, going back to basically the same concept, how a program is executing, we talked about the fact that the first step will be to actually put the content of the output of the program counter on the bus, right? That was the first step that we talked about it in the previous slides. So in order to do that, we need obviously the counter out signal. So counter out, and at the same time, we need to actually read that instruction into our memory address register. So that's why we have counter out memory in as the first step of every instruction in our computer. Now after that, if you, let's say, build Ben Eater's 8-bit computer, we normally go to the next step, which is step number 3. However, remember in Bravo, we actually have a concept of the high byte and low byte. So we actually have to repeat the same step 1 again, but this time we need to set the HI signal high. So that means that at step 1, we actually taking the low byte of the basically program counter on the bus, and then with the next step, we are actually taking the high byte on the bus. So we need 2 steps here. And finally, at step 3, what we need really here is just to do a RAM out, and then the HI and CME, as I mentioned here, means instruction in. So we do a RAM out, put the content of that specific memory address on the bus, and then we have an II signal or instruction in, which is again a combined signal. You need both HI and CME to be high, so that means that basically we have an instruction in. So this is the fetch instruction in Bravo. Now a simple example here would be, let's say, an instruction like LDI, and we're going to talk about those instructions in more details in a minute, but let's say that we're going to do a load immediate or LDI instruction in our computer. So as you can see, the first 3 steps are basically just our fetch instruction. Again, as I said, the fetch instruction will be the first 3 steps of every instruction in our computer, including LDI. So let's say that we actually executed 1, 2, and 3. Now, the final step really would be to load something into our A register, and that's going to be from the immediate next memory address, and that's the meaning of LDI, right? So LDI means that load a value from the immediate address or immediate next memory address into our A register. So assuming that we already have that value somehow set in the next memory address, what is happening here is just we doing a RAM out and A in, right? So RAM out, put the content of that memory address that have that value that we want to put it in the A register. And A in, basically, just read that value from the bus and put it into a register. Now, as you can see, we also have CEME, which means basically we are actually counting to the next step in the execution of the program. And finally, we have the IC, and that's a very specific signal that we have here. And we're going to talk about that in a minute. However, for now, just that's an extra signal that actually prevents our micro step counter from proceeding to the next step, and it's going to save us some clock cycles here. So we're going to talk about that signal shortly, but for now, this is really all the steps involved for an LDI. Now, if it has been a little bit confusing, let's have a look in more details and what is a program actually, right? So let's say that we are trying to execute a program to add two numbers, x and y, right? So if you want to write that in plain English, we could say we want to load the x value directly into a register, and that probably means that we're going to do an LDI. And the next step would be to load y value, which is a value in the memory from a specific memory address, and add it to our x value, right? So that normally means, the add instruction in our basically computer. And by the way, we will be building those instructions later in more details. And even today, we're going to talk about some of those. But for now, I'm trying to, go step by step and describe this program in plain English and then see how it actually translates into different instructions. And finally, the last step of that, because now we loaded x into A, and we loaded y probably into B register, our ALU actually doing the addition of those automatically, and the output will be in our ALU basically register. And then finally, we could output that into our output display, whatever it is. In our case, it's a UART. So let's see how this works. So first step, again, as I said, it's called load immediate, right? And if you look at it, this LDI part is called an instruction, right? And the second part is called an operand. Now, some of the instructions in our computer are going to have a 1 byte operand, like LDI. So with LDI, you're only going to have one operand, which is an 8-bit or 1 byte value that is going to be somewhere in the memory. However, some of the instructions, like instructions that are actually pointing to a memory address, like add instruction, are going to have a 2 byte operand. That means that we actually have two 8-bits back to back on the next memory address that needs to be processed somehow by our logic. And some of the instructions have no operand, like output instruction, which it just outputs the content of the bus into our, let's say, display. So depending on the instruction, the operand could be 1 byte, 2 bytes, or even no operand. Now the instruction itself, we normally call those, when we actually use those in programming, we call them mnemonics. And mnemonics are basically just used for programming, right? I mean, our computer is just understanding 0 and 1s, and obviously if we have an instruction like add or LDI, it would not be able to understand what does it mean. These letters that we use for those instructions, again, are called mnemonics and are only for programming purposes, so that we as humans would be able to write a program using those. However, these mnemonics actually needs to be translated into some values, binary values, so that our computer understands that, okay, this value is actually equivalent to LDI, or another value is actually equal to add, and so on. So that was really all about it. Now, another important point that I would like to mention here is in regard to the memory structure in Bravo. In Bravo, we will be using a little Indian format when actually addressing our memory. That means that when we have an instruction like add, and we are actually pointing to a specific memory address in front of it, we need to basically put the low byte first and then follow it by high byte. So when we are actually saying add 0180, that actually points to memory address 8001. I hope that it is clear. If you are not familiar with Little Indian format, just search it online and you will be basically find a lot of information about it. And then now let's have a look at the LDI10. We basically trying to load immediate value of 10 into our A register. Now, I just, kind of put the first step of actually this instruction here so that you get an idea how it's going to be executed. Now, the LDI10 essentially means that load a value of 10 from the next memory address directly into A register, right? And in order to do that, as you can see, we're going to come up with some signals to do that, right? So those signals will be outputted from our control logic and going to different modules and perform exactly what we need to do here. Again, for this step, which is LDI 10, the first step of our program, as you can see, the first 3 micro steps, what we call it, are really the fetch cycle, COMI, COMIHI, and ROHICME. We talked about it. This is the fetch instruction. And finally, the step number 4 is really what is actually loading that value of 10 into our basically A register. And as you can see, we're doing an RAM out, AN, CME, and finally the IC. All right, so let's go ahead and have a look at the last slide. I know that it's getting a little bit long, but I thought that all of those little details probably will be useful to you guys in regard to understanding the Bravo and how actually the microcode is structured. Now, again, as I said, the microcode is basically addressed through 13-bit output from the flag register, instruction register, and the microstep. However, those flash memory chips that we talked about actually are 128K, right? So in order to basically address those, we normally need 17 bits or 17 pins. However, since the output of our registers here are really 13 bits, we kind of have 4 bits, or the 4 most significant bits, which we are not using for addressing. And in fact, when we look at the circuit, you see that those pins are actually tied all to ground, meaning that we just set them by default to 0. So let's call them just filler bits, or bits that we don't care about them, and they will be always 0. So combining those 4 and plus 13 bits, which coming from here, gives us a total of 17 bits. And that's going to actually be used to address our ROM, or 17 address lines in our ROM. Now let's talk about the fact that each instruction in our computer is going to be assigned a binary value, right? We talked about that in previous slide, that our computer doesn't understand, let's say, letters LDI, and it has no sense of it, doesn't know what it means. So essentially, we kind of come up with a binary value for each instruction. And this is completely arbitrary, and you could pick any number, actually, any value, let's say between 0 and 64, because remember, we had only 6 bits for the instructions, right? So using that 6-bit, we could come up with 16 different combinations, and we could really put, pick any value for any of the instructions. However, I'm following the minimal projects, microcode design, and I will be using the same values that has been used in the project, because that makes sense when you look at later and look at the documentation for minimal and so on. So for example, for a load immediate instruction, we have assigned the value of 14. And that means that whenever we want to actually have instruction LDI executed, we need to set the value of our instruction register to 14. Or for another instruction like, let's say, store A, which stores the content of the A register into memory, we pick, let's say, a value of 21. So each instruction have a specific value associated with it. Now, if we kind of look at the table at the bottom of the page, so let's say that we first just going to look at the LDI instruction here, right? So LDI instruction, again, as I said, we're going to have a 4-bit. We just call them filler bits. We don't care about them. They're just, there because we, need have, 17 bits for addressing. So the next 3 bits are actually assigned to our flag. And as you can see here, I'm just setting all of those to 0. However, we actually, when we're creating microcode later, you notice that we actually have to come up with all different combination of those flags. But for now, let's just assume that all of those flags, we set them to 0. Now, if you look at the instruction column here, you see that all of them are set to the same value. Why? Because we are talking about the same instruction, right? So LDI has a value of 14 based on, our design here. So this is basically going to be a value 14 for all of those, steps. However, if you look at the steps, which is actually output by our, micro step counter here, see that the steps are changing from 0. That should be 0 here. That's a mistake. So it's going to be 0, 0, 0, 0, and the next one will be 0, 0, 0, 1. I'm sorry about that. But again, for step 0 to step 15, we're going to have our control signals, right? So for example, I talked about that step 0 in LDI will be in signal CO and then MI. Both of those signals should be active at this stage. And the next step, we're going to have CO, MI, and HI, and so on. So I hope that you get a basic understanding of how microcode works in Bravo. It's basically a combination of flag register, instruction, and the micro step. Combined together, it gives us a value, and basically for each step, we're going to have some specific signals active in that micro step. Now, as the last slide, if you think about it, actually, with all of those different combinations that we talked about, we're going to have 3 bits for flags, 6 bits for the instruction itself, and basically 4 bits for the micro steps. If you actually multiply all of those together to see how many different combinations we could have, we're going to come up with 8,192 total micro instructions. So that's actually 8K of instruction that we're going to have in Bravo. And that 8K instruction should be written into both ROM chips or both of those flash memories. All right, so with that, I know that it's a lot of material, and hopefully has been a little bit clear. But again, when we look at the circuit, and of course we go to testing, hopefully it's going to be more clear and make more sense. All right, and so as usual, before building the circuit, let's have a look at the circuit logic. And with the review that we had on the slides, the circuit should be quite easy to understand. So as you can see at the top section, we have our instruction register, which consists of 3 parts. The first part is our flag register, and as you can see, the inputs of our flag register are connected to 0 carry and negative flag that is coming from our ALU. This chip is basically a 74HC173, just a simple register. The output enable lines are already tied to ground, as you can see, and that means that as soon as we have a data on the input side, it's basically going to show up on the output pins. Now, to control this chip, we need a signal, right? And that signal will be basically EO or sigma out and FI. And if you remember, we talked about that signal. This is actually a combined signal that actually should be EOFI, but again, the FI part is actually coming to this chip and controls the basically input enable side of this chip, which means that whenever we bring that line high, it's going to read data from our basically ALU, and it's going to basically save those flags inside this register. So that part should be clear, and obviously we need a clock, and as you can see, the clock is coming to this chip. Now, the next part is our instruction register, and instruction register chip here is really a flip-flop chip here, which basically just get the value of the instruction from the bus, as you can see on the input lines, and upon the rising edge of the clock, which comes to the clock pin, it puts it on the output lines. However, there are 2 points here. So one is, if you remember, we talked about instruction in signal or II signal in the slides, and I mentioned that that's actually a combined signal of CEME and HI signal. And the reason for that is, as you can see here, we actually have an AND gate that is combining the CEME signal along with HI signal together, as you can see here on the screen, and basically outputs a value when both of those signals are high. Then the output will be high, obviously. And then on the next rising edge of the clock, we're again combining both of those signals through a NAND gate here that gives us a low signal. However, what we need really here is a high signal on the clock pulse. And if you also noticed, the second point here is that we actually have an inverter. And that inverter actually is very important because if you think about every instruction that is executing in the computer, we really want to read the instruction into our instruction register before the next clock pulse, before basically the clock advances to the next step. And that's pretty much true about all 8-bit computers that probably you are familiar with, including if you have built the Ben Eater's 8-bit computer. We were actually inverting the original clock pulse because we want that instruction to actually be executed before the next clock pulse, so that we actually read the instruction into our instruction register. So with that, I hope that it is clear that the control signal is II, and the clock signal actually coming here and is inverted before getting into that chip. And finally, we have the microstep counter, which is again very simple. It's a 4-bit binary counter using a 74HC161 that we have talked a lot about this chip in this project. And as you can see, all the input lines are tied to nothing, or basically no connect. And then the basically output of this chip will be really just a value between 0 and 15. Whenever we receive a clock pulse here, we're going to have a value. And as you can see, again, the same thing happening here. The original clock signal from the computer is actually inverted before reaching this chip, so that we are actually one cycle behind, or let's say ahead of the main clock pulse. And then the rest of the pins are quite clear. As you can see, the chip enable and the count enable are actually tied to high. That means that we are not reading anything from the from the input side, and also we will be continuously counting. However, an interesting thing here about this chip is that, as you can see, the master reset line, which is an active low signal on this chip, is actually coming from an AND gate. And that AND gate is actually fed with 2 other signals, which we're going to talk about that right now. So the first signal that is coming to this AND gate is actually our main reset signal for the computer. And our main reset is an active low. So whenever we want to reset the computer, we need to bring that signal low. However, in normal situation, that signal is high. So therefore, one of the inputs to that AND gate is high. However, the other one, as you can see, is coming from the output of our control ROMs, and specifically this signal is called IC. All right. So that signal, I think I have mentioned it in the slides, but let's have a look and see what it does. Basically, when we are actually doing counting here and going through all those micro steps from 0 to 16, or excuse me, from 0 to 15, what will happen is that if we don't have a control logic here, the counter will continue to the next step, until it reaches 15, and then it's going to basically reset to 0. However, if you think about a lot of instructions and basically micro instructions inside an instruction, you see that we actually not necessarily have 16 steps. Most of the instructions in our computer have less than 16 steps. Therefore, it would be great if you could somehow control the counter here, so that when we actually, let's say, have only 5 steps, the counter only steps up to 5, and from that point on, we just continue with the execution of the next instruction, rather than counting all the way up to the 15 and resetting the circuit. And that's exactly what is happening here. So with every instruction in Bravo, the last stage or the last micro step would actually be an IC signal. And that IC signal, as you can see, is combined with the main reset signal going through an AND gate. And basically, that's an active low signal. So that means that whenever we want to actually stop the counting on this and say, okay, this is the last micro step, and you could just stop right here, we could bring that signal low. And by bringing that signal low, we basically just make the output of this AND gate low, and therefore we are resetting that chip back to 0, or basically this chip will not be counting from that point on. So that's a great mechanism here, because we will be saving a lot of unnecessary clock cycles here, meaning that if a micro instruction is only 5 steps, we are really running this counter here for 5 steps, and after that we're just going to stop the counting by resetting the circuit. So that's a cool thing, and of course in order to do that we need one extra signal, which is called IC, but again, that is very useful since it could save a lot of clock cycles during the execution. Now, I hope that the input side of those chips are clear. Now, the output side of all these 3 sections, as you can see, are connected directly to address line of our flash memories. And if you look at it carefully, you see that, for example, the address line A0 is actually connected to step 0. So that step 0 is actually coming to least significant bit on our address line of our flash memories, and it's going to continue to instructions, and then after instructions we're going to have the flags. However, as I mentioned in the slides, these flash memories are 128 kilobytes, and therefore to actually address the whole memory you're gonna need 17 pins or 17 bits, right? But here we really have only 13 bits that are output of our instruction register part. So we have like 4 pins at the end, or 4 most significant bits on both of those chips that are really not doing anything. And as you can see, from A13 all the way up to A16, we're going to tie them to ground. So basically we're going to set those values to 0. And if you do that, essentially you're going to end up with only 13 lines to address those chips, and obviously you're going to be able to only address 8K on each of those chips, which is exactly what we want, right? So hope that part is clear. Now, in regard to the control signals, let's have a look into more details here. So the input sides, again, are connected to both chips, identical. For example, step 0 pin here comes to A0 or address line 0 on both chips. And that means that basically we are actually addressing both chips at the same time, which is fine. And the reason being is that each of those chips are actually responsible for a subset of the control signals, meaning that the most significant chip here will be output a couple of signals, and the least significant chip here will be actually outputting other signals. So since each chip has only 8-bit output, we could have a total of 16 signals outputting from this flash chips. Now, in regard to the signals that are outputting, if you look at the output lines, which are actually from D0 to D7 on each chip, you'll notice that each pin has been assigned a specific signal, and that's going to be our base signals. However, if you remember, we talked about that actually some of those signals are combined with each other to create new signals, right? So if you remember, we talked about that, for example, we have the TR signal as one output, and as you can see, the TR signal is actually the output from a D4 of the most significant byte chip here. However, if you look at it, this signal is actually coming into two AND gates here, and combined with HI and inverted HI to generate the TO or TI lines. So that means that for transmit and receive, what we're really outputting from the chips is a single TR and also an HI signal, which basically we combine them to generate the TO or TI. So the HI signal itself is coming actually from the chip on the right-hand side, which is the least significant byte chip, pin number D7. However, at the same time, using an inverter here, we are actually immediately invert that signal to inverted HI. And this is basically that famous inverter that I have been talking about in all of those previous videos, that when we have an HI signal, it's going to be inverted immediately and give us the inverted HI. So now we have two signals that we could play with and kind of come up with those combinations. Now, the rest of the signals should be quite clear. Most of them are single signal that goes to different modules. So you could probably look at this circuit in more details and see which signals are coming out of which chip. So now, if we really want to output something from this circuit, what we need to do is that we obviously need to read the flags from ALU, we need to read the instruction from the memory, and then finally we need to step our microstep counter, and the output of those is going to basically address our RAM chips. And then since we are going to program those RAM chips and define actually each instruction and each micro step for the instructions, then based on those inputs, we're going to output those signals on our control signal logic. So I guess that's really all about the control logic circuit, and let's go ahead and build it and test it. All right, so we built the control logic, and I guess we need to just test it now. Only thing is that before going into testing, we actually need to write some data and these LSB and MSB flash ROMs. So let's do that first. So I have to actually take out these chips and use either our minimal flash programmer to program them, or if you have a mini pro, you could use that as well. So either way, we have to actually write something on these flash. What we're going to do, we're going to have a look at a sketch and come up with at least a little bit of data so that we prepare this board for testing. And then once we wrote that data into flash chips, then we're going to come back and basically mount everything. All right. All right, so we're ready to test the module. However, before starting the test, we really need to write something into those flash memories. Because those flash memories by default from factory, they're all set to value FF on all memory cells, and therefore there will be no way to actually test those and see if they're outputting any signals. So at least we need to come up with some test instructions, let's say here, to just test if we are actually outputting any signals. Now, before moving on to the test instruction, let's just have a quick look at the structure of microcode once again, and this time using an Excel sheet. So I've created this Excel sheet, which probably could help us understand how the microcode is actually structured and how it is created. And finally, it's going to translate to a value that actually needs to be written into our flash memories. So let's go step by step. So, and I'm going to post all of the files, including this Excel sheet, into GitHub page, so that if you wanted to download it and just use it for demonstration purposes or for practice, generating the microcode using this Excel sheet will be a very tedious type of job if you want to do it this way, because again, you probably need to create like 8K of instructions, which will be a very long process. So later on, we're probably gonna develop some sketches and use some some code to, or either Python or let's say some Arduino sketches to generate those microcodes. But for now, for demonstration purposes, we could just use an Excel sheet to see actually how data is structured. Now, if you remember from the circuit, the four most significant bits were actually all set to 0. In fact, in the circuit, we tied them all to ground. And that's why we just have a column here, which have 4 bits in it, and all of them are set to 0. Now, that is followed by our flags, and basically that's going to give another 3 bits here. And then we have our instruction, which is 6 bits. And finally, we have our step. Now, I've created an arbitrary basically section here called no instruction, and that's actually doesn't mean anything, and it is not going to be uploaded eventually into our flash. However, I wanted to have this section here as a template, because that's going to help us in understanding what is the initial value of each signal. So when we have no instruction, essentially meaning that we are actually all our steps or micro steps are setting to 0, meaning that we don't have any output. However, this no instruction section could show us what is the status of each signal initially without that signal being active. So this section, the first section, as you can see here, from column B to column I, are actually showing our address lines, right? If you look at it again, 4 bits plus another 3 bits for flags, another 6 bits for instruction, and finally we have 4 bits for steps. And if we put those bits all together, we're going to come up with an address, right? And that's the address that we're actually using to address the flash. And here in this column, I'm just converting that binary value into a hex. So this column is really the addresses that we will be writing to, right? And the next section is actually the data that needs to be written into those flash memories. Now, if you look at the data side, I actually listed all the available control signals. So the first 81 are related to the most significant chip, and the following, the pink area, is actually related to the least significant chip. Now, these signals are basically matched exactly with the pins on the flash memory chips, meaning that, for example, the most significant bit on the most significant chip is actually outputting the CI signal, and that's why that order of these signals are important here. Now, if you look at the no instruction section, you see that I'm actually setting a 0 for all the signals that are active high. And that means that when a signal is active high, we need to bring it high. By default, the value should be 0, meaning that if we want that signal to not be active, we actually have to set it as 0. However, there are some signals that are active low signals, and for those signals, we actually need to set the initial value to 1 because we want the signal to be inactive. Essentially, this section is just setting every signal to its default value. However, an important point here is that in Bravo, for the signals that are active low, we are actually outputting low on directly from our control logic, and that's a little bit different than let's say Ben Eder's computer. If you have built Ben Eder's computer, when we were doing the microcode, we were outputting everything from the control logic as a high signal. So if a signal even was received by final module as a low signal, we were still outputting high on the microcode side, on the control logic. And then, if you remember, we had actually a section on the circuit that we had all the LEDs for the control signals, and Ben was actually using a couple of inverter chips there to invert the signals that needed to be an active low. However, in Bravo, if a signal is high, it just will be outputted high from the control logic, and if it is low, it's just going to be outputted as a low signal directly from the control logic. So now, let's say for no instruction, let's say we kind of set everything to 0 except the steps, which are actually incrementing from 0 to 15, and all other signals are actually at their default value. Now, as I said, no instruction doesn't have any practical meaning here. However, if you go to an instruction like no op, which has a value of 0 in regard to the instruction value, remember that each instruction should have a value. For example, no op in Bravo is going to have a value of 0, and let's say LDI is going to have a value of 14. So with, let's say, value of 0, obviously we're going to set all the values for instruction column to 0. However, for steps, you see that we are actually have different steps, and the value of step is going to change. And when we're combining all of those together, you see that we are actually coming up with different addresses. Now, a no op instruction in Bravo, and pretty much in any other computer, does not do anything really. I mean, it's just an instruction there. If you don't want to do anything in the computer, you're just gonna call upon this instruction, right? However, despite the fact it doesn't do anything, it still needs to have the fetch instructions, right? So as I mentioned before, the fetch micro instructions should be part of any instruction in the computer. So as you can see here inside the no op, we really don't have anything other than the fetch cycle, which consists of 3 steps. COMI is the first step, COMIHI is the next step, and finally the last step is really ROHICEME. And as you can see, the rest of the steps are really set to value of 0. Now, in this specific instruction, no op, we actually don't have the IC signal to stop the counter. And basically for no op, we're just going to go all the way to the last step of the micro steps. However, for all of our instructions in Bravo, we're going to actually end the instruction with IC. No op is just an exception here because we basically want to not do anything for 16 steps or 16 clock cycles. All right, so with that, if you look at it, in order to implement no op, what I'm doing here is that I'm looking at the steps, and for each step, I'm actually changing the value in the related column. So for example, in case of COMI, which is going to be the next step in our micro instruction, I'm changing the CO from value of 0, which is the default 0 if you remember, to a value of 1. And then I'm changing the MI, which is the memory in signal. Again, this is an active high, so we needed to set it to high. And that's it. That's basically, we covered the first step. And the rest of the signals just stay at their own default value. Now for next step, we're going to repeat the same thing, COMI. However, we also have the HI signal set to high. And so on. So we're just going to implement that step by step. So step 1 actually has 2 signals. Step 2 has 3 signals, and finally step 3 actually has 3 signals. Now, if you set those bits to high and low based on your micro instruction, what you end up with is really a row of bits, high and low, for both the LSB and MSB chip. Now, if we take this bit and put them together all in one cell here, as you can see, I'm just taking all of those bits and kind of put them all together here as a binary number. I could actually convert that binary number to a hex number here in this column. This column is really just the equivalent value of this binary number. And that gives me basically the hex value that needs to be written into our flash memory. So since we have 2 flash memory, we're going to repeat the same process for the LSB. So this part is actually the MSB part, and this part is the LSB part. And then when we convert those to hex, we kind of come up with 2 columns here that gives us the values that needs to be written into our flash memory. However, in this example, as you can see, I set actually all the flag values to 0. However, in the final version of the microcode, you actually have to come up with all combinations that these flags could have and repeat exactly the same instruction again and again for 8 different times. Since we have 3 bits and those 3 bits are actually could have 8 different combinations, you actually have to repeat the whole process and then change only the flag size so that we have all the combinations of the flags and instructions. So hope it makes sense here. Just for demonstration purposes, I'm only showing when the flags are all set to 0. Now, if you look at the LDI, it's basically the same. As you can see, LDI has a binary value of 14 in our microcode. So as you can see, the instruction column is actually set to value of 14 in binary. And again, steps are increasing. And then following the same procedure, we kind of come up with the address. And also, we're going to come up with the values that needs to be written into those addresses. Now, with all of that, I actually created a very simple test instruction, and this is really not a final instruction that is going to be uploaded to our computer. However, for our test, what I want to do is that I want to actually step the clock, and I want for each step to one of the signals be high. So that means that we are actually doing a very simple test here. And in this test, we're just gonna, pulse the clock in the computer. And with each clock, I want the signal to come up one by one. And we're gonna start, let's say, from CI signal all the way to the BO signal. So if we actually upload that to our flash memories, the expectation is that each clock, one of the signals are gonna come up, and then it's going to continue until it reaches the last step. So the instruction is quite simple. I started from the memory address 0 actually on both of our flashes. As you can see, we started from memory 0 all the way to memory address 15. And then what I'm changing is really just the value of the signals here. So at step 1, or micro step 1, essentially, I'm just bringing the CI signal high. In next step, I'm bringing the CO signal high, and next one CME, TR, and finally IC. However, in case of IC, since it's an active low signal, you see that I'm actually setting the value to 0. That means that when I actually want to bring that signal high, I need to set that to 0. And interestingly, this IC signal is actually an exception, and we're going to get into it when we're testing on the LED board. But just remember that for the signals that are active high, we set to 1, and for signals that are active low, we are setting those to 0. So again, very simple instruction, not a practical one, but at least it's gonna let us test our control logic. Now, if we upload that instruction to or this microcode to our flash memories, what we need to do is essentially just set those values and those first 16 addresses in both of our flashes. So for the MSB flash, we're going to just program this 16 bytes, and for our LSB, we're going to just program this 16 bytes. Now, in order to do that, I'm actually using a very simple Python script, which is here, and this is a quite simple Python script, which what it does, it just gets these values that we generated here, and kind of creates the bin file or the binary files that we need to write to the flash. So as you can see, for the most significant byte, I'm creating a byte array, and I'm basically just getting those values directly from Excel sheet, which is 0x89, which means that that's a hex value, and you can see we have 89, and then 49 and 29 and 19. I'm just going to write them into a byte array here. Now, once I created a byte array, this is really only 16 bytes, right? However, our flash memory is 128 kilobytes. So what we could do, we just kind of fill in the rest of the flash memory with FF, or just with the default value. So in order to do that, I'm creating another variable, which basically I'm adding that initial byte array that we created with data, and I'm creating another byte array. However, here I'm filling all the space with FF, which means that I'm kind of taking the length of this, which is basically just 16, and I'm subtracting it from the total memory space, which is 131,072 bytes. Essentially, that means that's a 128K. And then I'm going to fill in everything with FF. So the result is really the first 16 bytes will be this data, and the rest of the data on the flash will be really just FF. And then once I have that all saved into that variable here, I'm creating a MSB rom.bin file, and basically I'm writing that data into it. I'm going to repeat the same process, but this time for the LSB part of the data. And as you can see, I'm writing 1F, 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 just like here, and kind of the same thing. So executing this script is essentially going to give us two bin files, one for our MSB flash memory and the other one for the LSB. So let's go ahead and execute that and see what will happen. So if I do a dir here, I have my script there, so I could just say Python, and then I could just execute the script. And once we executed that, we are actually gonna have two output files, as you can see here, the LSB ROM and MSB ROM. So let's open them. Let's actually open the MSB ROM again with our Notepad++, and then if you go to hex view, you see that the first 16 bytes are actually the data, which is the data that we expect, right, for our MSB, written in a sequence here. And then the rest is really just filled with FF to the end. And if we actually open the LSP file, we should see the data for LSP content, which is 1F for first 8 bytes, and then followed by 9F, 5F, and so on. All right, so now let's go ahead and basically program our flash with this data. So let's go ahead and take out the LSP chip. And I'm gonna use our minimal flash programmer for the LSP chip. All right. I think it should be good to go. And if you have followed the flash programmer video, you probably have seen that I've already loaded a sketch on our Arduino Nano, so it's still there and I haven't changed it. So if you're not familiar with the flash programmer module, I would recommend that you go back to that video and watch that video. Otherwise, we could just, connect power, and now we are ready to program this flash memory. All right, so let's first program the LSP. So I have copied the prom.exe to this directory where we created the bin files. If you're not familiar with the prom.exe in flashing or programming the flashes, please watch the video for flash programmer and describing the details there. Another thing that I have to mention here is related to the COM ports. So let's see what we have here. So we have the files that we created, the bin files, and also we have prom.exe. So prom.exe essentially is the utility that we're going to use to program the flashes. And as you can see, we just need to say prom.exe and then type -w and the file name. The file name in this case is the lsp rom.bin, and if you hit enter, you notice that it is trying to actually open the COM port 1, and it's going to be stuck here, and it's not going to basically do anything. Unfortunately, with prom.exe, we could not specify the COM port, and maybe your flash programmer, just like mine, actually has been detected on a different COM port. So in fact, if we look at the device manager here, you would see that I have multiple devices connected at the same time on my Arduino, and I have the default COM port from the computer, and I also have the flash programmer. So in this case, it's gonna just go ahead and pick up the first COM port that it's gonna find, and it's not gonna work. So what I'm gonna do, I'm gonna abort that, and basically I'm gonna disable COM port. So you just write on your device manager, you click on the COM port and disable that, and then if you have any other devices connected and they're taking COM ports, you could either temporarily disable them, or you could unplug them. So in this case, I have my Arduino plugged in, so I'm gonna basically unplug it. And as you can see, the only option that is left right now is really COM port, which is connected to my flash programmer. And now if we actually run prom.exe, it will be able to pick up that COM port, and as you can see, it just started programming. So that's something that you need to consider if you are using the flash programmer and the COM port. Make sure that you leave only one COM port active here, so that the prom.exe will go and pick that up and start programming. So if you see that it's actually saying writing, then basically it's working. We just wait for that to finish, and then it also gives you a little bit of a checksum at the end. So here we go. We have 0 errors, and it just read about 8K of the RAM, and looks like everything is good. All right, so we programmed the LSB. Now let's go ahead and program the MSB using MiniPro. All right, so now that we have programmed our LSB chip, let's go ahead and do the MSB chip. Well, for this one, I'm gonna use my MiniPro, just to show you guys that we could use either of those devices. So I'm gonna take out the MSB chip here, or MSB flash ROM here, and I'm gonna use my MiniPro flash programmer. Actually, could be the other way. There we go. And now we just need to connect our USB cable to it. And let's go ahead and program this flash memory as well. All right, so for the MSB chip, we are gonna use the XG Pro application, which comes with your MiniPro. So if that's a brand new chip, it's probably erased and has the factory default value. Otherwise, you could just click on the erase and just erase your chip. And then we're gonna load the file. For this one, we just use the MSB ROM file because we're trying to program the MSB. We're gonna open that file, and if you open it, you'll see that that's actually the data that we want to write to the flash. And then the next step is just basically click on the program. Before that, you just want to make sure that you select the right chip here. This one is obviously SST39SF010. I've already selected that. If you don't have that option here, you just click on this button and find the manufacturer and the model here. Yeah, let's click on program, and that's it. So to verify it, after writing to it, you could just do a read, and basically that should show you that the data is actually written into your flash. All right, so now that we have programmed both flash memories, let's go ahead and put them back on the board. And I'm gonna put the MSB on the MSB socket. As you can see on the PCBs, we have, if you can see it on the camera, yeah, we have MSB and LSB should be at the top. All right, so this is gonna go to the MSB socket. And of course the other one, I'm gonna be a little bit careful here with those chip pins. All right, so this one is actually an LSB chip. So now let's go ahead and mount that to our Arduino shield. And finally, I'm gonna connect the LED board, and we should be ready to go for testing. So finally, I'm gonna connect the power to the whole system, and let's see the sketch and how we could actually test this module. All right, so I loaded the Arduino sketch here, and as usual, we have some functions that are initializing and resetting the board. So the main functions are actually starting from here, and this sketch is quite simple. We are not really doing anything other than pulsing the clock, and the reason is that we want to actually the control logic to output our control signals, and basically everything should be done by control logic, not our sketch at this point. So let's have a look and see what's going on here. So in the main setup function, I'm actually gonna set all the pins related to the control signals to input. So by default, when we are defining those, we are essentially doing kind of resetting all those pins and set them as a default, and basically kind of bring them either high on or low based on their default value. However, all of those signals are actually set as output initially, because for the previous sketches, we actually needed to write into those pins. Essentially, we need to bring those signals high or low. That's why we set them all to output. Now, in this sketch, we actually have to reverse that and set all of those to input pins. Because if we leave them as an output port, Arduino essentially will be controlling those pins, and we would not be able to actually see any signals on those. Therefore, the first thing that we're going to do, only for the control signal pins, which I have listed here, we're going to set all of those into input, except one pin, which is the IC pin, and I'm going to talk about that in a minute. So this is the first step. And then there's really one function which says test control logic, and inside test control logic, we just count from 0 to 15, and essentially with each count we're going to pulse the clock. Okay, now let's see why we actually have an exception here for the IC pin. So as I said, every pin should be set as input. However, this pin still needs to be an output, and actually we have to make this pin high. So if you go back to this circuit, you remember that we had an IC signal coming out from the most significant chip. This signal is combined with the main reset signal on our computer and essentially going through an AND gate, and the output is basically going to our microstep counter, and essentially this is the signal that actually keeps this counter active or counting. So what will happen is that if we actually set this IC chip to input, what will happen is it's going to keep that line low, and since this will be low at that point, it's not going to count all the way up to 15. So the idea here is that really to pulse the clock, and each time we pulse the clock, this microstep counter will be counting, and it's outputting a different address on the output lines, and the combination of this address and the output of the instruction register and the flag essentially will be addressing a different location on the RAM. And obviously we specified through our microcode or test microcode that with each microstep one signal will be outputted from those chips. Now if we keep that line high all the time, what will happen is that we could see actually all the steps or microstep being executed here. So that's an exception here, and I guess that's a little sacrifice that we have to make. We will not be able to see this signal actually going high. However, obviously if the counter is counting and it continues to count all the way to 15, that means that that's actually working fine. Again, so the sketch really, there is really nothing into it. We just have a manual pulse clock, and this function is just pulsing the clock one by one. All right, so let's test that. And now let's actually upload it to our Arduino. Now, as you can see, it will actually start counting the microstep counter basically, and with each count it's going to change the address, and as you can see, with each clock pulse we are actually outputting one of the signals, and that was the objective of our test here. So let's reset it one more time so that we could see it. So you see that it's actually with each step except the IC signal, which is here, and we had to just keep a high. And why we don't see it here, why the LED is not up, because we're still setting it as an output pin basically in our Arduino sketch. So we'll not be able to show that. However, the rest of the signals obviously are outputting fine from our control ROM. So this is really a very, very simple test, just to test that, okay, our instruction register is actually able to address our flash memory, and we see all the control signals are outputting fine. Obviously, you could be more creative and come up with more comprehensive test case here, and you could, probably attach your memory module or program counter and kind of test everything together. However, here I just really try to simplify the test and just do a very simple test because essentially we're going to load the operating system and the programs in the next video, and that's going to be a full test of the computer. So hopefully with this simple test you're verifying the control logic, and in next video we're going to have a full-fledged test on the whole computer and every single module. Alright, I hope that you guys enjoyed this video. I know that this one was a little bit long, but I had to actually go through some details in regard to describing the microcode and how our control logic works. Now, the point is that you could actually go ahead and start exploring control logic and developing some microcode. So the plan here is that to actually, in next video, as I said, we will be loading the minimal operating system and also all the programs, the assembler, into computer. We're going to stack all the modules together, and basically we're going to do a full test of the computer. However, after that, I may actually start making a couple of more videos in regard to developing microcode, or maybe further going into developing opcode and so on. However, I guess at this point the hardware is complete and ready, and you could actually explore a lot of areas in this computer. I'm gonna post a file, and it is basically the list of all the opcodes and basically microcodes that has been developed for minimal CPU system. This is again part of the minimal project by Carsten, and he has developed an extensive list of basically instructions, as you can see here, that are all functional, basically 64 instructions and so on. So you could actually go through them and try to understand them one by one. For example, no op, what is right now the microcode for it, or we looked at this one actually, we look at the LDI and so on. So the rest of the instructions are available for you to look at them and trying to understand them. But again, going through them individually and trying to write a program, I guess it takes probably a little bit of more time and maybe a couple of more videos. All right, so with that, I'll see you in the next video.